questions. I have your second assignment ready, and I have the projects almost done, so I'll post it up maybe end of this week, and then you will have a week to go through and then sign up. Many of you have your own ideas for projects. That's fine. Yeah.
You may do something about the project you're proposing. Did you get my email? I mean, did you see it? It was long time ago, maybe a week or two.
Yeah, I have it.
Maybe, yeah.
Yeah. Okay, so the second assignment is about two types of problems that one we talked about, one we are going to talk about today. That is ordinary differential equations of the initial value type and boundary value type. And this is a very famous model that was derived from the Navier-Stokes equation, fluid mechanical problem, convection in atmosphere. And there is a whole book devoted to properties of solutions of for this equation. The equation itself was discovered only in the 70s, but there was a flurry of activities in trying to play with this, and this was done through computational means, the so-called strange attractor. So it's a introduction through example. What you'll have to focus is on learning MATLAB and using ODE 4.5, which we have seen, and I have uploaded all those MATLAB files as well in the Moodle. You can download them and adapt them for programming this particular problem. And there are three cases, sets of parameters that I ask you to do, 1, 2, and 3. In one case, it will go to a steady state. It's a transient problem. In one case, it will go to a steady state. In the second case, it will go to what is called a limit cycle. That is, it will go into an orbit forever. No matter where you start, it will go to that orbit. And in the third case, it will go to what is called a strange attractor. And it will be nice to see whether you can plot that and try to figure out where it goes in the state space. And we'll talk about these when we talk about a couple of lectures on dynamical systems theory. And the second problem is what I'm going to talk about today on boundary value problems. How do we solve that? And using that, you solve a particular problem, which is a second order ordinary differential equation, nonlinear. But BVP 4C is a tool that we are going to see today in MATLAB. We'll also see it in COMSOL. Okay? So the tools that we will see in MATLAB have a parallel in COMSOL, but they are relatively easy to use both in MATLAB and COMSOL. But the moment you go for partial differential equations, MATLAB becomes a more difficult tool to use, and then we will easily switch and continue to develop our expertise in COMSOL. Okay, so expect this to be up in the Moodle sometime later today, and you will have a week to work on these two problems. So in the last lecture, we basically looked at FSOLVE to solve the CSTR problem, two nonlinear algebraic equations. And then we also saw how to solve it in MATLAB for the dynamical problem, which is using ODE 4.5. The same problem, but when you have transients on its way to a steady state. So we perturb the system to see whether it will go back to the same state. And we saw that in one parameter set, there are three different steady state solutions. So all these complexities we will cover in a more systematic manner. We are just learning how to use the tool. That's the focus on giving you enough introduction in MATLAB and COMSOL so that you can get started for your project and as well as assignments. And we saw the same problem under steady state condition in COMSOL. And today what I'm going to do is, this is the problem that we studied. I'm going to talk about the next problem, which is heat transfer from a fin. It's a fairly simple problem. What you have is, this is the kind of fin that you will see if you open up your desktop computer on the top of CPU, central processing units, because the CPU generates a lot of heat and you want to dissipate that to keep the CPU cool. Same thing in car engines and wherever you have engines, you have this dissipative heat transfer mechanism. So in this particular case, you have a base plate which is at a temperature of T0, that is hot. And you have one extended surface like this. The goal of providing the surface is to provide faster heat transfer mechanism. More surface means you have more heat that is lost through that. And you may actually in reality have many of them stacked one besides the other like this. Okay, but we are taking that for the analysis just one. Okay, and we set up a steady state energy balance in this case, and that is what you would have seen in undergraduate heat transfer course. There are a number of parameters that are defined. T0 is the base temperature, and T infinity is the ambient temperature. I guess I don't have it somewhere. Here you have. So yeah, here. Okay, and L is the length of the fin from the base to the tip, and A is the cross-sectional area that you see. If you cut the fin, you will see an area, and it is that area through which conduction takes place, and that area is appearing here and here, etc. Okay, and there is some heat that is lost to the surrounding by convection mechanism. Often you have a fan blowing on top of these fins. So that conduction heat transfer is modeled by a heat transfer coefficient multiplied by this driving force that you see here. Okay, so H is called a heat transfer coefficient, which is a parameter which depends on Reynolds number, the velocity, etc. Okay, but in our case, we are going to just take some constant numbers to see. The goal is to see what kind of model arises out of this, and why is it called a boundary value problem, and how do we set it up for solving in MATLAB and then in COMSOL. Okay, so the energy balance statement is this: rate of accumulation equals rate in minus rate out plus rate of generation. Okay, rate of accumulation. Now we define this as a steady state problem. Okay, so the rate of accumulation is 0. And rate at which energy comes in to the control volume. So you have to identify what is the control volume. The control volume is something like this. Okay, so you're taking a thin slice. Let me just erase that. The shaded area that you see, this is thin volume of thickness delta x. Okay, through the left side there is energy that is coming in by conduction heat transfer. But from the right side, it is leaving also by conduction heat transfer. So that is modeled by Q times A. Q is the flux, so many joules per meter square second. Okay, and so when you multiply it by the area, you get joules per second. So much of energy that is entering from the left face, and the same quantity evaluated at the values at the right hand side. I guess I should probably blow it up so that you can see that. Okay. So the right hand side is evaluated at x plus delta x. Then there is energy that is transferred to the surrounding ambient air, because these are the 4 surfaces that you have bounding our control volume. And it is a one-dimensional problem because we are saying that there is no variation in this direction. The variation occurs only in the x direction. Okay, that is from the base of the fin to the tip of the fin. Because base is maintained deliberately at a hot temperature, so heat transfer is in that direction. So if you take 2 points on these sides, they don't have a gradient in temperature, so there is not going to be an energy transfer. Would you challenge that statement? You can, when you are near the edges, right? But as long as it is a thin, long fin, we can assume that it is one-dimensional. Okay. Otherwise, in COMSOL, it's very easy to extend from 1D to 2D. In MATLAB, it's not. Okay. So, so the energy that is transferred to the surrounding, we're saying, is modeled by HP times delta x. P is the perimeter, that is the distance measured going around, and multiply that by delta x gives you the surface area that is exposed to the air. P times delta x. And H times, there must be a T minus T infinity. T is the local temperature at this particular point, and it is a function of x. And T infinity is the ambient temperature. Okay, so that's what we are saying here, that statement. Okay, so this is the energy coming in from the left side, energy leaving the control volume from the right side, energy leaving from the top and the bottom, and maybe a little bit from the edges. Okay. Any questions on those? So this is a statement where we are taking a conceptual statement of the problem, identifying a control volume, applying the conservation of energy principle, translating the concept into an equation. That becomes a model. Okay. So any questions on any of these terms?
So if there is a fan that is blowing air from bottom or something like that, how would this equation change?
This equation will not change. What will change will be the parameter h. because H is a heat transfer coefficient. So you will have a Nusselt number as Reynolds number to the power B, Prandtl number to the power C. Reynolds number will have the velocity in it. So the way to change the convective heat transfer is by a fan is to change the heat transfer coefficient. And we will see what happens, what is the impact when you change the heat transfer coefficient.
So they're trying to make this problem one-dimensional? That's why you
We are-
use delta X?
We are trying to make this one-dimensional, but once you learn the tricks in COMSOL, it's so easy to make it two-dimensional. When it is two-dimensional, what would happen? You will have to have a bounding box in the y direction, perpendicular direction, and you will have QA at y and QA at y plus delta y, and so you will have a second order derivative in the x direction and in y direction. So it becomes a partial differential equation. Okay, any other questions? So the next step in going from here to there is essentially divide everything by delta x, okay, and take the limit of delta x going to 0. From the definition of the limits, you know that this two terms is nothing but the rate of change of q times a, and then you have hp times t minus t infinity. Okay, and then substitute for q. Q is given by the Fourier's law of heat conduction, okay, minus k times gradient of t in the general case. Okay, so q is a vector and gradient of t is a vector. K is a property. Now that's a phenomenological model. This statement is a conservation law for energy, but q equals k gradient of t, we call that as a phenomenological model in the classification of models that we saw in the very first lecture. Why do we do that? Because not all materials need not obey this. Okay, it simply says empirically all the experiments that I have done shows that the amount of heat flux is proportional to the gradient, and the proportionality constant we define it as k. Okay, now when it doesn't fit, what do we do? When it is not linear, for example, if you plot q versus delta t and it's not a linear, you say maybe thermal conductivity is a function of temperature. Okay, so you try to develop that data at different temperatures and try to fit k as a function of t. Okay, so that there is a lot of empiricism involved in proposing a model like that. But once you accept that empirical model for the so-called Fourier's law of heat conduction, the same thing is true for Newton's law of viscosity and Fick's law of diffusion. All these have a parallel in the sense they capture processes that are taking place at the molecular level. Energy transfer by conduction is basically by molecules vibrating, and they're not moving in bulk, they are staying in the same place, but they're vibrating and transferring the energy to the neighboring molecules, right? So molecular processes giving rise to macroscopic phenomena, diffusive processes. All of them are diffusive processes because they affect only the neighbor, so that effect propagates through affecting the neighboring molecules. So when you take that and plug it in here, you're going to get in one-dimensional case. This is the 3D version of it. So in this case, you will say qx is minus k dt dx. Okay, substitute that and you get a single ordinary differential equation. Okay, and if k is constant and if a is constant, a is the cross-sectional area, right? In the problem that we sketched here, we are allowing the area to change with distance. Do you think it's a good idea? It is a good idea. Why is it a good idea? Because once you have lost some heat from there, the remaining heat is less to be transferred across. So you need a smaller area. So you can put a uniform area, but then what happens is you're carrying unnecessary weight. Okay, particularly if it is in a mobile unit like an engine cooling fence, then you're transporting that, right? So to optimize the material used in designing an efficient fan, you actually may pose the problem in such a way that the shape is unknown and ask what is the least material that I need to transfer a certain amount of energy. So an optimization problem can be built on top of that. But in our case, we will just take A to be a constant so that we can take these out and then put them in non-dimensional form. Now, this is a second order equation because it has second derivative in temperature. Temperature is the unknown. Temperature is a function of x. and H and P and K and A and T infinity are all known parameters. And there is another known parameter, that is the length of the fin, that doesn't appear in this equation, but it affects the problem, right? The length of the fin will determine the efficiency. Where does it occur? It occurs in the boundary condition. So the parameters in a problem can occur either in the differential equation or in the boundary condition that goes with it. Now, this is a second order equation. So is it linear or non-linear? It's linear because the unknown is t, and there are no non-linearities in t. You don't have t to the power 4. If you are looking into radiation heat transfer, then you'll probably have another term that will be sigma to the t to the power 4, radiative heat losses, right? Then it will become non-linear. But for now, the temperature appears by itself, so it is a linear problem. It's a second order problem. So when you integrate it, you will get two integration constants. You need two boundary conditions to evaluate. Now, what's the difference between initial condition and boundary condition? If for a second order equation, I give you both the conditions, the auxiliary conditions at the same location, then it becomes an initial value problem. Like in the CSTR problem, concentration and temperature at time equal to 0 was given. And then you have a marching problem and you integrate in time, as long as it reaches steady state or some sort of an equilibrium state, limit cycle or whatever. Okay. In this case, we are saying that x equal to 0, the temperature is T0 at the base of the fin. And at x equal to L, that's where the other parameter L appears, right? At x equal to L, the temperature is T infinity. At the tip of the fin, it's at room temperature already. That need not be true always, okay? But that's one possible boundary condition that we can specify. An alternate boundary condition, I should have added an R here, is at x equal to L, that is at the tip of the boundary, it is insulated. That means there is no heat loss. That means the gradient of temperature is 0. So both are possible, okay, at the other boundary, at x equal to L. So this is one boundary condition. This is the second boundary condition. One of the two, okay. You can impose.
Same, right? If you don't have any extra insulation, then that's the same condition.
If you don't have any extra insulation, then
those two are the same boundary condition, right? It's just writing it differently. Because the temperature equals to T infinity and then no.
Well, it's a good question. Okay, let me just make sure that I understand your question. Okay, when the tip is not insulated, will T always be equal to T infinity in reality versus what we impose? Here we are imposing a boundary condition, so you will get a solution that meets those boundary conditions. So you can always impose that T is equal to T infinity at the tip, and you'll get a solution with that. Okay.
I meant to say, like, those two boundary conditions, the second and the third one, it's basically the same thing.
They are not the same thing. They are applied at the same location, at x equal to L. The meaning of that would be different once you see the solution. Maybe since you raised it, let me just plot it.
I'm thinking, like, if you don't have any extra insulation, then saying no slope means the T has to be equal to T infinity in the S, right? If you don't have any extra insulation, then only the slope can only be 0 if.
How about this? The gradient is not 0. The temperature is not T infinity also, right? So it depends. If you put T infinity, then the solution would be like this. The gradient won't be 0, but the temperature will be driven to T infinity. But you can set it to any other value. Okay? But in reality, what happens, if you have a very, very long fin, or if you have such a large heat transfer coefficient that all the heat is dissipated before you reach the fin tip, then the temperature will be T infinity. So as you change the parameter H, for example, or as you change A, it's actually a combination of dimensionless numbers that we will see, you will find that the temperature profile can be like this. If you get a temperature profile like that, what it says is your fin is useless in this part. You are carrying unnecessary material because nothing is happening there, right? So your design should be in such a way that it reaches T infinity and the gradient also reaches 0 at the point, right? Then you have dissipated all the heat and you have a cool tip, right? But you cannot specify both. because you don't have the degree of freedom. You can specify only two boundary conditions. One is already specified at the left boundary as T0. So you have only one other boundary condition on the other side, right? And this is where you can use other parameters like A. In fact, if you make A as a function of X, that is a variable fin, then you gain extra degree of freedom as a designer. Then I can ask the question, okay, what should be A of X such that I can meet this dual condition of temperature being room temperature and the gradient being 0, right? Any questions? Is it clear? Okay, so we are not treating this essentially as a numerical course. We are also looking at the physics of it, modeling. Okay, as I said, trying to come up with the best model is an important part of this course. Okay, so if there are no questions, then what I'm going to do is try to put those equations in dimensionless form. Okay, that is, this equation becomes this. How do I do that? I define a dimensionless distance psi, which is scaled with respect to L, x over L. So when x equal to 0, psi is 0. When x equal to L at the tip of the fin, psi is equal to 1. Okay, so, and similarly I define a temperature, a dimensionless temperature, as T minus T infinity divided by T0 minus T infinity. So at the base of the fin, what is T? T0, right? At the base of the fin, theta should be equal to 1. That's what I'm writing here, because T will be T0, right? At the tip of the fin, it might be T infinity. So the lowest value that I will get is 0. Okay? But as I said, that can be one boundary condition. The other boundary condition is the derivative at psi equal to 1. Sorry, that should have been at the base, psi equal to 1. Okay? Should be 0. The derivative is 0. Now, in doing this in dimensionless form, what I've done is I've taken Ka outside and divided throughout by Ka. Okay, so I got rid of that Ka. And then when putting this in dimensionless form x, I'll get an L square in the denominator. I take that to the numerator. So I have a new parameter which I call M, and that is HP L square over Ka. It's a combination of all those dimensionless parameters that determines the efficiency of the fin. Okay, so you can achieve the same efficiency by having a very large heat transfer coefficient, or a very small thermal conductivity, or a very small area, etc. Very large fin length combination that gives you the same M will have the same efficiency. This is the beauty of putting things in dimensionless form. Now in COMSOL, you cannot really do that because everything, and in Fluent also, everything is done in dimensional quantities. Okay, but we will see how we can use tricks to make it. We have to do this work on paper to put that in dimensionless form, and then we will use the template in COMSOL to solve that. Okay, so this is the problem that we are going to solve. It's a boundary value problem, and you will see how easy it is to solve in COMSOL. In MATLAB, you need to begin to do a little bit of extra work, because MATLAB has a function called BVP4C that solves boundary value problems. But you need to convert this second order equation to two first order equations. So you always need to convert. If you have a very high order equation, fourth order equation, sixth order equation, you need to convert them into an equivalent 6 first order equations in the case of a sixth order, 4 first order equations in the case of a fourth order, etc. So here you need to convert that into 2 first order equations. How many of you know how to do that? If I give you this problem and say convert this into an equivalent problem that contains 2 first order equations. No? You haven't seen that before? Only one person. Huh?
I've seen it, but can't remember.
Cannot remember it. Then you will, if you've seen it, you'll remember it.
Like through substitution?
Through substitution, through creating additional variables. Okay. So what we would do is we would say y1 is equal to theta and y2 equal to theta prime, or d theta d psi, the derivative. Okay. Then you will say, okay, what is y1 prime? Y1 prime, this is the definition. Now we have to derive 2 equations for y1 and y2. Then we will have 2 equations. that eventually mimic exactly this, reproduce this. Okay. So when I take the derivative of the first equation, I get y1 prime equals theta prime, but theta prime is the same as y2. Okay. That is my first equation. I will call this my first function. The first function gives me an equation for the variable y1 in terms of the function f1, but the function f1 turns out to be simply y2. Okay? And the second equation will come by taking the derivative of the second variable. Okay? That is going to be y2 prime, which is going to be equal to, oops, what's happening? Theta double prime, right? y2 prime is, when I take the derivative of this one, it's going to be theta double prime. But what is theta double prime from this one? M theta, right? It's going to be equal to m theta, which is going to be equal to m y1. That will be my function 2. Right? So I have two equations in two unknowns. y1 and y2 are my two unknowns. These are two first order equations. And f1 is y2. The first function that goes with y1 is f2. The second function is m times y1. So these are coupled because y1 is affected by y2 and y2 is affected by y1. Okay? Now I need to convert the boundary conditions also into this form. Okay? And what we need to do in MATLAB is write a function that takes y1 and y2, returns f1 and f2. Just like we did in fsolve and just like we did in ODE 4.5. You write a function that defines what your problem is and that takes a vector consisting of y1 and y2, returns a vector consisting of f1 and f2. Okay, and we will see how to do that. Now, what will be the boundary condition? The boundary condition would be, if you take this, it will be simply theta is y1. So y1 at 0 equal to 1. And the other condition, one of them would be y1 at 1 will be 0, or y2 at 1 will be 0. Because y2 is theta prime. Okay? So we need to pass these boundary conditions also into MATLAB. And then MATLAB enforces the boundary condition and the differential equation and gives you a solution matching those. I don't know, am I making a mess on the notes? Or you guys? When you are focused on what I'm writing, it's fine. But when somebody comes into this room and sees, it's a mess. Right? And I keep erasing it from time to time. So I'm not very organized, even when I use a blackboard. Okay, any questions?
So the A is like changing with X or not? Yeah.
In this particular problem, I've assumed A to be constant. So I've taken A out. Okay, and if A is changing with X, I need to prescribe that function. And then it becomes a differential equation with a variable coefficient. MATLAB will handle it in exactly the same way. If you do it, this you can do analytically very easily. Just write the characteristic equation. It's a second order, you get two characteristic roots, and you know what the solution is. But if I put a of x there, analytical methods fail. You need to have a series method solution because you are an expert in those things. Your supervisor is, right? But numerically, computationally in COMSOL, in MATLAB, it's exactly the same thing. You just program that function. If it is 1 minus x squared, just put 1 minus x squared, saying that it varies like that, and then you have the function.
Technically, on that shape, A definitely varies with respect to X. I mean, given the shape, technically, A definitely varies with X.
I mean, there are fins of all kinds. You have fins that are just constant thickness. In this sketch, it varies, right? But they have shown it. But in the problem formulation, I let it vary in this step, but I made it constant in this step. Okay, it's an assumption I have placed just to keep things simple to illustrate. Okay. Any other questions?
Isn't it easier to solve this using something like symbolic math?
This is a linear problem, so the simplest way to solve is characteristic roots and analytically. Okay, but what we are trying to do is learn how to solve it in MATLAB and COMSOL numerically. Now, you are right. There is another set of tools that we haven't talked about. We probably won't talk about in this course. because it's about numerical methods, right? So, but they're symbolic tools. So you can use Maple, Maxima, Mathematica. There are a whole range of tools that will try to construct a solution analytically for this. But analytical solution can go only so far. Because the problem gets nonlinear, there is no way, except in the asymptotic sense. Okay, you can say, okay, what is the solution in the when m is very small or m is very large? You can construct those asymptotic limits, but to span the entire parameter space, you have to use computational methods. Okay, and yeah, so there are other tools available. Those that know for this problem, I think you can use it. But the problem that I've given you in the assignment, Mathematica will choke and Maple will choke because there is an e to the power theta nonlinearity in that problem. That problem also has a lot of multiple states and stability issues that we'll talk about later. It is coming from a combustion problem where there is a heat of reaction that has an exponential term. Okay, so let's start. Which one would you like to see first, COMSOL or MATLAB? MATLAB?
Easy to transition.
The thing is, if you see it in COMSOL, you wouldn't want to use MATLAB for this. MATLAB, you need to do more work. You need to do more work. Let's just start with MATLAB then. The hard way first, right? So remember, what we need to do is we need to understand. We'll just open up the BVP4C. That's a function that solves such problems, and try to learn how to pose our problem for this. Okay, it's called BVP4C. Now, BVP standing for boundary value problem, and the 4C simply says it's a fourth order collocation method. Something that we are going to see later on. What method? How does it? How do all these algorithms from FSOLVE to ODE45 to BVP4C work? We will learn later on in terms of numerical methods. But I just want to know how to set up the problem right now. Okay. I don't know whether I can blow this up. Okay, it works. So the way to use this, the syntax for this particular function is BVP4C, and then a function name, which is very much like what we did in FSOLVE. You write a function and you give it a name, and you pass that name here. But you also write another function where you pass the boundary condition. So they call it BC_fun. Okay? So a function that returns the boundary conditions, a function that returns the differential equation to BVP4C. So once again, we will write the code, pass control to BVP4C, and BVP4C will interrogate these two functions to get the solution, to construct the solution in between, enforcing the boundary condition. The boundary condition is actually enforced in a very generic way that you will see in this function. And then there is something called SOLINIT, okay, and that is the initialization for the problem, and that you do through another function called BVPINIT. So conceptually, what it does is you have a variation in one spatial dimension. Ordinary differential equations, boundary value problems have essentially one variation, one spatial dimension. So you need to discretize that, meaning I cannot solve unless I use Maple or Mathematica. I cannot get an analytical expression for theta as a function of psi. So I need to get solutions at discrete points numerically. Okay? So I need to define what that grid looks like. Maybe I should have started it with COMSOL, because you will see the process in COMSOL visually. Okay? But in MATLAB, you need to define what that initial grid distribution is through that vector. And similarly, you need to specify the initial values for your state variables. Now we have formulated as two variables and two unknowns, y1 and y2. So I need to specify what is y1 as a function of x in the entire length, and what is y2, which is theta prime, as a function of x over the entire domain, 0 to 1. Okay? And the third one is any other parameters that we can pass. And similarly, there is an optional fourth parameter that will control the residuals, the errors, etc. Okay, so that's basically what I need to do, to call the BVP4C and tell it there are two functions and these are the initial guesses and this is my grid. Okay, you need to specify all these to BVP4C. Okay, any questions on that? Now, when you open this for the first time and read this, it may not be, you need to spend half an hour to an hour reading through this and trying to understand and maybe look at an example at the end. Typically, they do have, see, they have a detailed explanation of how to specify the BC fund, and we need to come back and look at that as well. Okay, and how to specify the sol init and what are structures. We will learn a little bit more about MATLAB, and so the description begins here. Okay, so you need to read all these to kind of understand how to set up the problem. It's done in a very generic way. Okay, y prime equals some function of f, x, y, p. P is a set of parameters. X is the independent variable over which the distance changes. In our case, it is 0 to 1, but it could be 0 to L, whatever the length is. And y is a vector. So you can have any number of differential equations, okay, that are boundary value problems. And y prime is its derivative. So it is presented as a system of first order equations. You should always convert a higher dimensional system to a system of first order equations of this form. That's your model. And the boundary conditions are also specified in a very generic way. Okay? That is, some linear combination. In our case, we have one boundary condition at the left, another boundary condition at the right. But it doesn't have to be like this. It's just a constraint. So you can have a function that's a linear combination of what happens on the left-hand side or what happens on the right-hand side. Or even a linear combination of the two variables on the left-hand side. In fact, we should probably talk about that, something called the Robin boundary condition. I don't know whether you have seen that. So in this case, let's just see some terminologies. When you have a value specified like this, it's called the Dirichlet boundary condition. Okay? When you have the derivative specified like this, it's called the Neumann boundary condition. When you have a combination of this, it's called the Robin boundary condition. So you can have, for example, alpha times theta plus beta times theta prime, all evaluated at x equal to 0, is some constant, gamma. Gamma can be 0. Okay? So in this case, if gamma is 0 and beta is 0, alpha is 1, you get your original Dirichlet boundary condition. If gamma is 0 and alpha is 0, beta is 1, you get the second boundary condition. But the boundary condition can be as general as this or even more complicated nonlinear function. Okay? And MATLAB will handle those boundary conditions. But we need to learn how to specify those, how to write the two functions. The first function that models, that programs this, and the second function that models this. Okay? Any questions? Once you see it, you will understand the logic, I think. And I will upload this also so that you can use that as a template to solve your particular problem. So this is a function that I wrote, and I wrote a main driver and two sub-functions. The two sub-functions, one evaluates the differential equation, the other evaluates the boundary condition. Okay? So the main function is just a driver, so it doesn't have any input or output, but I still give it the structure of a function by declaring it as a function. Why would I want to do that? That allows me to put the two additional functions inside the same file. Okay? Or I can make this into a script. If I make this into a script, that means I just comment that out, then it treat it as a script. But it will complain because I cannot embed a function within that. I need to put these functions outside this file in the same directory for it to find these two functions. The first function is just called fin. Position it so that you can see all of them. Okay, so function f equals fin xy. Okay, x is the independent variable, y is the vector of dependent variables. Y has two elements in this case, y1 and y2. Y1 is theta, y2 is theta prime. Okay, and I initialize a set of parameters. Heat transfer coefficient 2.5, perimeter 1, length is 1.5, etc. And I calculate m from the formula that I have. And then these are the two lines. So it's really not a very difficult program to write, right? Because I already know that f1 is y2 because we developed that. When we converted that in here, for example, the y1 prime, the first equation is just f1. The f1 is y2. And the second equation is theta double prime, which is the function f2, which is m times y1. Okay? So the second function that you will see here, f2 is m times y1. So what is going to happen in this function, whenever BVP4C calls this, it will pass values of x and a vector of y1 and y2, but it will actually be a matrix, right? y1 containing theta values, all the values of x, and y2 containing theta prime, all those values of x. Okay? But this x is never used here. Why? It doesn't depend. This model doesn't depend on x. When will it depend on x?
So y already has x, right?
No, y is a function of x. That means y will be given at various locations. Okay? Are you following? My question to you is, the generic way that the function is written, BVP4C will pass two values, both arrays. Okay? One will contain the location of the independent variable x, and we can actually pause and see what numbers come in. The other one contains a matrix, 2 by 10 or 2 by 20, depending on how many bit points you have. Okay? But the x is never used here. And my question to you, if you understand this process, when will x be needed inside that?
Non-linear problem.
Not necessarily nonlinear problem, because x is an independent variable, right? In the problem that we have seen, if the area is constant, right? If the area is changing with x, that information will come in there. So you will have here not a as a constant, but you'll have a function 1 minus x squared, and it needs to know what value of x is to evaluate that area at that location of x. Okay, that's where it's very nicely constructed, so that you have a most general linear, nonlinear, constant coefficient, variable coefficient. Everything will be handled by the same formalism. Okay, so any questions on that function?
So y comprises of theta and
Theta prime. Theta and theta prime as two vectors, but packed in one. So it will actually be a matrix. In fact, let's set a breakpoint here to see what that matrix looks like when it comes in. Oh, thank you. Okay, so that's the main function. The other one is the boundary condition. Okay, how is the boundary condition structured? So here you see twin BC is the function that I write, and in the first case it's supposed to return f1 and f2, two function values. In this case it's supposed to return the residual, because the way that the MATLAB told us to construct this function is BC as a function of y of 0 and y of b is equal to 0. That means when you have a boundary condition, you need to write the boundary condition as left-hand side minus right-hand side equal to 0. Okay. So what do I mean by that? For example, if I go back to, it's really cluttered. I'm trying to focus your attention. So if I had this Robin boundary condition in MATLAB, how would I do that? I would do that as this minus this is equal to the residual. That means that the left-hand side minus right-hand side in general for any guess while it is solving won't be 0. But it needs to know how far away from 0 it is, so that it can adjust the solution to make it equal to 0. So it expects a residual back, and then it's its job, the BVP4C's job, to drive that residual to 0. Okay, is that clear? So you can have this on the left-hand side or the right-hand side. Okay, that's how we need to formulate the boundary condition. So with that understanding, does this make sense? So what we are saying is the residual is going to be a vector because there are two boundary conditions. So each condition will have a residual. The first boundary condition is theta equal to 1 on the left side, right? So YA is going to be a vector consisting of two numbers. But A refers to the fact that it is on the left boundary, and B refers to the fact that it is on the right boundary. Okay? So each one will contain two numbers. But we can use if there is a need. But in this case, all I know is that YA, that is on the left boundary, the first vector is theta. Theta should be equal to 1. That means theta minus 1 should equal to 0. Okay, that's one condition. So this will be one residual imposing our boundary condition. Is that clear? If not, please ask me. Okay, YA and YB are vectors. YA is a vector on the left boundary. YB is a vector on the right boundary. On the left boundary, you have theta and theta prime. On the right boundary, also you have theta and theta prime. At every point, you have theta and theta prime. Theta is Y1, theta prime is Y2, right? But what we have to impose on the left-hand side is nothing about theta prime. Theta prime can be anything it wants to be. But we want to impose theta is equal to 1. That's why we put 1 here. And the YA is the one that tells that it is the left boundary. And similarly, the second equation, YB says it's on the right boundary, and the first vector is theta. So what am I imposing there? Theta is equal to 0. If you want to change that right boundary to insulated boundary, what will you change here?
2.
YB2. Right? If you say YB2 and leave it as such, it will impose the derivative boundary condition on the right hand side. Okay? Any questions on that? So this is the job that we have to do for every problem that we are solving. Boundary value problem of any order with any number of boundaries actually. Right? You can have not just 2-point boundary value problem, you can have multiple point boundary value problem. It will still handle that, the kind of a residual, right? But we need to prepare the problem and write these two functions before we can call them and get a solution. Now, this is the main function that's going to call and get us the solution. Okay? So here I have sol init. So I'm using the function that's provided to me, bvp_init. And if, as you recall from the previous one, this is the grid points. I'm saying my domain, this is how I tell the problem, but my independent variable domain is from 0 to 1. Otherwise it won't know, right? All it will know is the two functions and the two boundary conditions. So I'm now specifying it goes from 0 to 1, but as an initial grid, take steps of 0.1. So it's going to construct a grid at 0, 0.1, 0.2, 0.3, 0.4, uniform grid to 1. So about 11 grid points or so. Okay, and then the next one is the initial guess. Okay, so it says for theta or y1, take the value to be 1 and assume the value to be 1 everywhere. Okay, you can provide a vector if you want, but if you provide just two numbers, it says, okay, I'm going to take the first number and assign it to y1 and set everywhere on every grid point as equal to the same value. It's only a guess, right? It's going to correct that guess to satisfy the differential equation. That guess will not satisfy. Well, that guess will satisfy the differential equation, wouldn't it? If I put a constant theta, if I make that theta as equal to 0, it will satisfy the differential equation because the derivative is 0, second derivative is 0, theta is 0. So, but it will not satisfy the left boundary condition. It will satisfy the right boundary condition too, but it will not satisfy the left boundary condition. That's the driving force. Heating is starting from the left side, okay, which makes physical sense. If you have a fin at room temperature, theta is 0 everywhere initially, and then you start heating the base, the heat is going to start developing from the left side to the right side, right? So the second one is the guess for the second variable y2, which is 0 because I'm specifying constant temperature, so the gradient is 0. But both are only initial guesses. Okay. Then I call BVP4C and store the solution in a variable called SOL. And the way I pass the function name is @fin and @finBC. Both are functions that I wrote that you see here at the fin and then the finBC. right? And then sol init is the variable that it constructed using the grid and the initial guess that I gave. In fact, let's set up a breakpoint there and start running it. And after that, it's just a matter of plotting it. Yeah.
So if you call a function inside function, then we have to do add, because before we just call a function and the at the rate sign.
It has nothing to do with the fact that the function is inside it. Even if the function is outside, you will still use that at sign to indicate that it is a function. It's a the MATLAB has a syntax, a way of explaining that, why they use that syntax to
But
address
this is different than what we did before, right?
No.
Like
No, we always had this.
whenever we call
FSOL we had it, and in where are those lectures here? Yeah, I see at sign there.
If you had created both these functions as independent functions separately, it would still do the same operation.
Yeah. If you save them outside in a separate file, each one an individual file, then you still do that. Okay, so any questions? Let's run this. I mean, it has done nothing, but it's staying in 11, so I'm going to execute that. So it has made a call to BVP init, and it did something and returned a variable called sol init. So I want to understand what this sol init is. So I take the cursor near it and say it's a structure, and it has all these variables inside that. Okay, so this is a neat way of packing related variables to a variable into something called a structure. Okay, so to address, for example, sol init.x, if you see, there are 4 things that are listed under this. Sol init.solver stores the string. Sol init.x stores these 11 numbers. Sol init.y stores these 2 by 11 matrix. Okay, and sol init.yinit stores these numbers. So it's a way with one variable sol init that is used in the next line. With one variable, you can pass all these information to BVP4C. So it's called a structure. Are you guys familiar with that? Have you seen it before? Those that have seen MATLAB, you would have seen that, right? So for example, I can say sol init.x, and I'm asking what is that variable, and it gives me these 10, 11 numbers going from 0. So that's my grid, 0, 0.1, 0.2, 0.3 in the independent variable x, right? So what would I get if I do sol init y?
So we'll get 1.
Y is the dependent variable, the vector, right? So that contains y1 and y2. Okay, y1 is theta, y2 is theta prime. So it has guesses for those. And the guesses, theta is 1 and theta prime is 0 everywhere. So these are all at every grid point. This is at x equals 0, at point 1, at point 2, at point 3, etc. Okay?
So we can understand sol init as a structure that has a collection of variables.
Collection of variables that you can individually address if you want by putting dot with the next one. Okay. Any questions?
So this BVP4C, is it using the finite method to?
It uses something called a collocation method, and we are going to see later in the course.
It's different than like.
Collocation methods are methods where you propose a test function, and that function is not exactly a solution to the differential equation. So you try to find the best values of the coefficients that multiply the function. So for example, if you take Chebyshev polynomial or Legendre polynomials, these are polynomials that are varying in x. So there are a whole series of polynomials, polynomial of degree 1, degree 2, degree 3, degree 4, etc. So you can write it as a0 times p0 plus a1 times p1 plus a2 times p2. So you are constructing a 4th degree polynomial, but your a0, a1, a2, a3 are unknowns. So you find what is the best value for these, so that when I take that test function, put it into the differential equation, the residual is minimized. And you do that by collocating at a certain point. That's why it's called the collocation method. Finite element method, collocation method, they're all kind of variants on that we will see later on. Any other questions? Okay. Next, we are going to call and transfer the control to BVP4C. Okay, so when I execute this, I think I have set up, sorry, where am I? Oh, that's not the one. This is the one. Yeah, I've set up a breakpoint inside this fin. I'm not directly calling fin. Okay, the control goes there when I execute the next one. How did the control come here? BVP4C is sending values of x and y and asking what are the values of f1 and f2 for this. Okay, so if you look at x, it gives you only the first point. It says, tell me what is the value of function f1 and f2 at that value of x. Okay, and y is 1, 0 at that grid point. So it's going to now calculate those functions, and so you'll have these two numbers, f1 and f2, and those will be sent back to BVP4C. Okay, and then now the control has actually gone into BVP4C inside because I was stepping through it. Now I'm coming back to it with a second time. Again, the same value. I don't know why it does it twice, but now it's coming with the value of x equal to 0.2 and the current values of y1 and y2 at that point. This will go on millions of times between BVP4C and this function. Okay, but it should also happen to the residual, and we haven't seen that. So let's do this. So it's going to evaluate at every grid point all the way, and then it will come back to the fin BC, right? So if you look at what is x now, 0.65. Now 0.65. Does that trigger an alert in you? Can x be 0.65? We didn't create a grid point at 0.65. We created it in steps of 0.1. Okay, this is something that you learn. So BVP4C has something called automatic refinement of the grid. So if it finds that 10 grid points are not enough, the error is going to be high, it will automatically put additional grid points. So when you find at the end of the solution that vector x, which initially was 11, might be 45 or 105 or 1000, okay, depending on how sharp the gradients are. You need to evaluate the gradients, right? So it resolves those gradients automatically for you. Okay, let me take this out. I think you understand it. You can play with it and continue to see until it comes here. Because I want to understand what is the structure of the data that comes in here.
Yeah, I was thinking to solve for functions, you have to go to the boundary condition as well. So I was thinking
You need
go
to.
both.
Right, yeah.
But
So
here
what?
it just went to the first one.
That's because it was trying to evaluate at every grid point. Once it finishes that, then it says, okay, now I'm going to minimize. That is, it finds a residual in the functions at every grid point, and then it finds a residual in the boundary, tries to minimize alternatively. Okay, so it's coming with value of 1 and 0 for the left boundary, and coming with 1 and 0, and it expects to take back residual, which is two numbers, right? It hasn't calculated, now it has calculated. So these are the residuals that you take back. One of them is actually satisfied. The residual is 0. The other one is not satisfied, right? So it is to drive the right-hand side residual to 0. Okay, so let me take that out and continue. And there's your temperature profile, right? So this part is generated by, after it solves it in here, I'm just plotting it. I'm plotting it using sol.x. Sol.x is the x variable, okay? And sol.y1 is the temperature. If I put sol y2, I'll get the temperature gradient. And the colon here indicates take all the values in that column. And here this says use a symbol circle and a line, so you get both. So there is your solution. So here theta is 1 on the left boundary, theta is 0 on the right boundary, but theta prime is not on the right boundary, right? On the right boundary, theta prime is a very large finite value. That means it is going to lose some heat through the Any questions on that?
So you're saying if you just change the YB minus 1, like YB2,
In fact, that's what I'm going to do
then
next.
It's gonna give a curve.
Right. So let's save that. Now I'm imposing insulated tip boundary condition. Okay, and then I will solve this. So that easy. You do it analytically, it will take another half an hour. You can solve it because it's still linear, right? But what you see here is that the tip is hot now. It's not at T infinity, right? The tip is hot, but the gradient is 0 because it is insulated physically. So there is no way for the heat to lose, right? Now, if I want to still drive this temperature to 0, what can I do? Increase the length, increase H, any combination that will increase your M will do that. Okay, so let's just increase H and see what happens. Where do I have it? 25 instead of 2.5. Did it not take?
Yeah, it changed.
It went slightly down.
It went slightly down.
It was in 0.65, it went in 0.1.
Oh, okay. So it needs really a large value.
Yeah.
There. So if you really blow a lot of air over it with a high-speed fan, that's how the fan will perform, right? So any questions? It is a bit of work in MATLAB because you need to write these functions and prepare the call. But I have, I guess, maybe I don't need to show all this in great detail.
So will you post all this MATLAB script?
Yeah, I will do that. I will do that. Yeah, this one. So I'm going to ask you to kind of look at this and tell me what I'm trying to do in this problem. It's the same fin problem. I'm solving the same thing.
Oh, you're varying H.
I'm varying H, solving for a number of different values of H, which we did so elegantly in COMSOL by just creating a parameter sweep. Okay, and you specify the range. Here, I need to declare a list of variables I want to change for H, and then find the length of that list so I can change any number here. Okay? And it counts how many are there and sets up a loop for each value of n. Okay? And for I equal to 1, it will pick the first value. So from the H list I, put it into H. And I'm using this number in the function. Okay?
That's what the global H function.
So I'm passing the value of this H through global because I need to change this. I need to set up a loop, right? I need to set up a loop. So and this function, previously I had H equal to this here. But this function is going to be called by BBP forcing many times. So I cannot really change the value of H inside this. So I set it up outside and change it systematically, but through this global mechanism, I say this variable is global. So wherever this symbol appears, pick up the value. So here I just need to declare this as global H, and it color codes it for me. So H is global, H is global, but its value is not assigned inside this. Its value is changed in the main calling program. So this is for various values of H. Okay. If there are no questions, yeah. Explain what's happening here.
Yeah, like different H, what does that really mean? Like,
Oh.
what's the meaning?
What does it mean physically? You need to go and understand this equation. Okay.
Faster heat transfer.
So if H increases, that means the mechanism by which heat is lost from the fin to the surrounding That's what this mechanism is, convective heat transfer. That's increased. So the fin is cooling much more quickly. From the base temperature of 1, its temperature is decreasing, but if I increase H, it's going to decrease much faster. Whereas if H is small, then it takes a longer length for the temperature to decrease. And that's what you see in this figure. In all these figures, like this one is H equals maybe 0.5, whereas this one is H is maybe 50.
It's
Right?
like using different material.
No, H is controlled physically by the fan that blows air over the fan. Okay, H is related to the heat transfer coefficient, which is related to the fan speed. Okay, but there are other parameters that you can change to have the same effect, because as I said, it's not H alone, it's not K alone, it's a combination of here you see H P L square K over A. So if I increase H by 10 times, or if I decrease K by say 10 times, it will be exactly the same effect. The temperature profile will look exactly the same. Okay? So that's what you meant, not the program. Okay. Any other questions?
Yeah. What change do you have to do for variable area? Just add, function of x equals to.
That's a good question. Maybe we'll have.
So the constant will change, right? Because we took out A out there and put it into N. That will no
Right.
longer be
So you cannot do that. You have to be a bit careful in handling a variable A. And what you need to do, if I can.
find another dimension.
Okay, so if I have dx of k, a of x, dt dx minus hp t minus t infinity equal to 0. So a is not a constant, but k is a constant, right? So you can take k out and maybe bring k here.
dy squared by L squared also.
But you need to expand this. So you need to write this as a of x d square t dx square plus dt dx times dA dx minus hp over k t minus t infinity equal to 0. Okay? Now you need to convert this second order equation to a set of two first order equations. You know how to do that.
Yeah. So you can't just add a function of x in the MATLAB code.
You have to. You have to figure that out.
And you have to first change this equation into.
No. You have to change this equation into this form, and then you have to say y1 is t and y2 is t prime. Okay, and then you will have dy1 dx is y2 and dy2 dx is your second derivative, d square t dx square. So that's going to be this. So then you will have to move everything to the right hand side in this and find out what the second function is. This is your first function. That function will be the same as before, but the second function will change. What will it change to? It will change to hp over k t minus t infinity minus y2 a prime over a. I guess I have to have a everywhere, right? That's it. Do you follow? So I've taken ax, divide everything, and then the second derivative is dy dx, dy2 dx, and so that is hp t minus t infinity divided by k by a, but this a is going to be a function of x, and minus y2 times a prime over a. So when MATLAB gets that value of x inside that function, it will use it to calculate these things, a and a prime. So you need to have an expression in MATLAB. If I'm beating it to death, tell me, I'll stop. You got it? Got the idea? Or huh?
Yeah.
All of you got the idea? Okay.
And the boundary condition also changes in this case, since
The boundary condition doesn't affect the A doesn't affect the boundary conditions.
Okay.
Yeah. The boundary conditions, the variations can be the Robin boundary condition, where I have mixed derivatives, The function and the derivative. Okay, but otherwise we looked at Dirichlet and Neumann condition, but you can implement a Robin boundary condition. Okay. Let's see how easy it is to do it in COMSOL. I have only 10 minutes. Let me try it. But you need to know some terminology. Like when we started with MATLAB, you need to know that there is a function called BVP4C that's appropriate for this problem. You need to read the manual to figure out how to set up the problem. Okay? And same thing will happen in COMSOL. So you know what equation you want to solve. What is that equation called in a generic sense? Have you heard of Laplace equation, Poisson equation? What would you call that equation? If you have to make a choice between Laplace, Poisson, Helmholtz equation, which one would that be? How does a Laplace equation look? How does a Poisson equation look? In 2D, in 3D, you have seen that, right? So a Laplace equation is del square t is equal to 0. Okay? And the del operator here can be d square dx square plus d square dy square plus d square dz square. Okay, operated on t is equal to 0. That's a partial differential equation. So it can. This is why it's easy to generalize in COMSOL, right? Because it solves this problem. In 1D, you don't have this. You just have one-dimensional variation. A Poisson equation is the same. Del square t equals some q. If you have a constant on the right hand side that's not 0, then you call that as a Poisson equation. So if this operator is one-dimensional operator, that's our template. Okay, so you need to find a matching template in COMSOL to set up your problem. Now, COMSOL has made it easy for you. For example, if you're doing fluid mechanics, there's a fluid flow module. If you say Navier-Stokes equation, that's your template. It pulls out the continuity and momentum equation. You define your geometry, you do the meshing, and set up the boundary conditions, initial conditions. It solves it for you. Okay? So the same thing has to be done for this particular problem. So I will build a model wizard. Instead of 0D, I will pick 1D because I have a variation in one dimension. Okay? And then I need to find the model that will correspond because it says select physics. So I go to mathematics and I look at classical partial differential equations. Here you have Laplace equation, Poisson's equation, wave equation, heat equation. Let me just pick. Poisson equation and heat equation will probably be the same. Okay, let me just take the Poisson equation and add that physics. Okay, so I picked my physics that represents my equations. Then it says study. What kind of study you want to do? We have already seen that. What are the possible studies? Stationary, dynamic, eigenvalue problem, etc. In this case, I'm going to pick stationary, and I'm done. So because I picked as 1D problem, it tells me a one-dimensional variation here. Now I need to define a geometry. In 1D, it has to be only a line. Okay, in 2D, it can be a rectangle, a circle, whatever, in a two-dimensional case. But in one-dimensional case, the geometry is going to be essentially a line. But it may put in the folder all the necessary folders that I need. Okay, so definitions, the geometry, the Poisson equation, the type of study. I need to pick the initial and boundary conditions. So the process is I first define my geometry. Okay, and the way that I define my geometry is by going here for interval. When I pick interval, it says left edge is at 0, right edge is at 1 by default. So I just say, okay, I'll accept that and build the object. So it immediately puts a line that goes from 0 to 1. That's the x-axis or a side axis for that. And it doesn't show the whole thing, I guess, there.
Number of intervals.
Number of intervals is the next step. That's called mesh. This is just the geometry. The geometry defines your domain. In 2D, in 3D, it can be very complicated domain. and it has access to CAD programs, so you can import a very complicated aerodynamic geometry from a CAD if you want into COMSOL. Question?
What was the difference of the previous equations that we used the zero dimension, but here we're using one dimension? What was
When you have zero dimension, it says that there is no variation in any spatial dimension. This is what we call the lumped model. So things can be either constant, homogeneous everywhere, or it can be varying with time. Like in the CSTR problem, even though you have a reactor, the assumption is every place inside the reactor has the same composition and same temperature. It's not true, but it's an assumption. Okay? So in this case, for example, we talked about, will the temperature vary in the second dimension? And the answer is, in general, it will. Like, will the temperature vary along this direction? But it's going to be, if the length is large, the variation is going to be small, except near the ends. Right? So it's a one-dimensional assumption. If it is two-dimensional, then you build this particular geometry, import it into COMSOL, then activate a 2D, and pull the same Poisson equation in 2 dimension that it will solve. Okay? So here is the mesh, and let's go and say build the mesh. And it by default, just like in MATLAB, it puts 10 grid points. Okay? But it also gives you some control, physics control mesh, and element size is normal. You can go and say make it finer, or make it extremely fine, which uses fuzzy logic, fuzzy terminology here, right? So you have now 100 nodal points over that domain. Okay, that's extremely fine. We can make it extremely coarse and build, and it has 3 grid points. This is going to have a lot of error. Okay, you can imagine that the temperature profile was like that. If you have 3 grid points, you're saying approximate each one by this. So that's going to be great error. So let's stick with finer and build that. Okay, so you have built the geometry, you have built the mesh, you have the equations there, and the domains are labeled for you. One, for example, there's only one domain in this case, and the domain is highlighted. So you need to specify the boundary condition. So you click on the equation, right click, it tells you all the available boundary conditions. So Dirichlet. Then it adds a Dirichlet folder. Okay, and I want to add another Dirichlet boundary condition because I have 2 boundaries. So when I pick on this Dirichlet boundary, currently it's empty. But if I go and click on the left boundary, there, it added 1 there. It again labels them. Boundary 1 is the left boundary, and I can give it a value here. The value is 1. Okay, and then click on the right boundary and associate it with this grid point. Come on, there. It's slow. And then associate it with 0. Right? Its temperature is 0. So you have defined the boundary conditions, you have defined the geometry, built the mesh. You need to specify what else? The equation. Right? The equation has a form like this. Do you see here? Gradient del dot minus E del U equals F. U is our unknown temperature, and F is our convective heat transfer term that we need to model. Okay? And if you want to model K as a function of temperature or A as a function of X, you plug all these through C. C is now set to 1. Okay? But you can put in a function there to model variable area, for example. Okay? If it is known. Okay, what else do we need to do? We need to define all the parameters H, K, A, and P. And for that one, I go into the global, right click on variables, and then I read the parameters from this file. I've already stored it. So there you have. Okay, the H, the P, the L, the K, and A, and I calculate M as a function of using the formula. Am I done?
So you said this programs you have to be dimensional, right? We can't use M and theta.
Well, I'm mimicking now dimensionless because I'm not giving any dimensions, right? So, but it doesn't know. As far as it is concerned, it associates a dimension with every variable that you have. For example, this has clear it of 1 over m squared because that matches the del operator.
And also that f is a constant, right? But in our equation we had f is t del t.
Right. So that's not, the problem is not finished yet. So by default, f is put as 1. To simulate our problem, f must model m times u.
Okay.
M I have already calculated in the parameters, and u is the symbol that it gives for the unknown. Okay, and I have a minus c here, right? And if I put a minus there, then I bring it, I will have this del square u minus m u equals to 0. Are you following what happened there? Now I have completed the problem for this. Okay, so I can go to study and then say solve, compute. Right click on the study and compute. Yeah, this this problem occurred to me earlier too. So the problem is h is an internal variable. Somewhere in grid spacing, I think it uses the same variable. So it doesn't like when I use h. So I just make it as HH. Those kind of frustrations with programming. When somebody writes a program, you need to know exactly what they mean, right? So you need to live with that. So let's go and try to compute again. There is your. So you can see the log. The log shows the residual is 10 to the minus 16. So it's converged. And you can see the temperature profile. Exactly the same as the one that we got from MATLAB. From 1 to 0. Okay. Any questions?
I don't really understand the equation part. Like
The equation part?
Minus and multiplied by u.
So the equation is illustrated here. So this is the equation. We want to make this equation look like our equation. Okay. So if I put f equals minus m times u, then what happens to that equation? There are minus on both sides. You cancel it out, and then you take that m times u that's on the right hand side to the left hand side, and c is 1. So it is essentially del square u minus mu equal to 0. That's the one we want to solve. So essentially we are making our problem fit one of the templates that they have. COMSOL is essentially that too. They have templates of partial differential equations for all kinds of problems. And you make your model fit that, and then it solves that particular problem for you. Okay? I think you kind of run out of time. So now you know parametric sweep and all that you can do on top of this to solve for different values of h, different values of k, whatever that you have. And the best part is if you want to make this from 1D to 2D, go back, pick a 2D, but you need to build the geometry and import it. The equation is going to be exactly the same. The del operator now becomes a Laplacian operator in 2 dimensions. Okay? All right, so the next assignment you'll get a chance to play with these kinds of problems in both COMSOL and MATLAB. Oh, there is one thing I wanted to show, the report. In MATLAB, you saw how to generate a report. So in the results at the bottom, there is a report folder. Okay, so you select the report folder, and then you can select brief report or complete report or intermediate report, and it produces a report for you in HTML or Microsoft Word. Okay, so and then you just say write, and it writes the report and saves it as a file. And if you open that file, you will find that it has all the information nicely with a table of contents. I just discovered this last night preparing for today. It gives you the parameters, everything that's in the folder on the left side. It opens up the folder and prints it out for you. Okay, so the variable name. So it's nice for you to submit the report as your. So this is the geometry, and then you see the grid points and finally, I think you will see the solution as well plotted. Dirichlet boundary condition. Write the Dirichlet boundary condition. Oh, I didn't realize it was producing this long a report. There is your solution. Okay, so have fun working with. Oh, sorry.
You mentioned that we can import some figures and geometries from AutoCAD to
Yeah.
console.
Yeah.
Does the license in the computer lab have that or not?
That's a good question.
I don't think we have.
I think we have a campus-wide license for ComSol Teaching Kit that has all, as far as I know, all the toolboxes, including the CAD ones.
Even link with MATLAB.
Link with MATLAB, link with CAD programs also. But the person who arranged it, do you know Professor Doran Boulder? Doran Accenter, right? Biological engineering. So he arranged the campus-wide, college-wide license. And so if you have any questions about licensing, he or the person that implements it is Chris Schwein in College of Engineering. He is the guy in charge of computers. So if the license goes down, as it did this morning at 5 a.m., I emailed him. By the time I came here, it was up and running, I think. So these are the two people that you need to know. Okay? I hope you find ComSol to be easy enough, and so that it allows us to focus on the physics of the models and the numerical methods as we move on into the course. So see you on Monday, but expect an assignment from me today to keep you busy. Yeah.
Based on mathematical or?
No, it's a numerical one. It arose out of MATLAB PDE toolbox, and it was initially called FemLab because it uses finite element method, and then it became ComSol. And